Today we're going to find out the molecular orbital diagram for a diatomic neon with a positive charge. So first we're going to draw out the valence atomic orbitals for neon, and we're only going to do the valence because the inner orbitals will not interact enough to create a molecular orbital. So we know that the 2s is all filled, and that will give us 1 sigma antibonding and 1 sigma bonding. 2s, and then we have 4 electrons. Okay, now for the 2p level, we know because it's a neon, it's a noble gas, all the electrons are filled. And we know because this is neon, so for oxygen, fluorine, and neon, the order will be a little different. So usually for period 2s, it's usually pi is lower in energy than sigma. However, because it's a neon, oxygen, fluorine, their bonding molecular orbitals will have sigma lower in energy than pi. Okay, now how many electrons do we have for 2 neons? We have 2, 4, 6, 12. But because this is a neon plus, that means it lost 1 electron. So instead of drawing 12 electrons in here, we're only going to draw 11. And that is the molecular orbital diagram for a diatomic neon plus. Now, some questions that they will ask you is to write out the configuration of a molecular orbital, such as a valence molecular orbital configuration. So you're only going to do the valence starting at 2s. You're not going to do the 1s or anything because inner electrons will not interact enough to form molecular orbitals. 2s. Antibonding sigma with 2 electrons, and then sigma 2p with 2 electrons, pi 2p bonding with 4 electrons, and then pi 2p antibonding with 4 electrons, sigma 2p antibonding with 1 electron. That is the configuration. Other questions they will ask you is to identify the lowest unoccupied orbital, which would be, you would just look at which one up here is unoccupied, but in this case it's all occupied. They will also ask you what is the highest occupied molecular orbital. So you just look at the highest orbital that has an electron. Now we'll talk about the shapes of these molecular orbitals. They have different shapes. So because we know that sigma is an end-to-end overlap of p orbitals, so you can get a bonding sigma orbital, which looks like this. Positive, negative, negative, in phase. Bonding is in phase, so. And then, or you can get an anti-bonding, which will have a node. Looks like this. This is plus, sorry. This is plus, this is negative. So this is destructive interference. And that is anti-bonding. Sigma bonding, sigma anti-bonding. As for pi orbitals, it is a side-to-side overlap. So it can get you a bonding and an anti-bonding pi orbital. Sorry, let's do bonding first. So it will look like this, where you have one node in the middle here. That is a node. This is positive, this is negative. And for pi anti-bonding, it will look like this. And there are 2 nodes here and here, axial and equatorial. Positive, negative, negative, positive. So these would be the shapes of molecular orbitals. If you wanted to know sigma s, 1s, sorry, sigma s or 2s, whichever you want. You see these are p orbitals. These are p. And then for s, it would just look like For bonding, it'll just be a circle. For anti-bonding, it'll be 2 circles. Okay, those are the shapes. And now one more question they will ask you is this neon diatomic plus paramagnetic or diamagnetic? So paramagnetic means there are unpaired electrons and that will attract magnetic field. And we see that here there is one unpaired electron. So because there is one unpaired electron, it is going to be paramagnetic. If all of its orbitals were filled, it would be diamagnetic and repel magnetic field. Okay. One more question that they can also ask you is bond order. So bond order of a molecular orbital diagram is a little bit different. So it is calculated by the number of electrons in your bonding orbitals minus the number of electrons in your anti-bonding orbitals divided by 2. So we'll look at our bonding orbitals. We have 2, 4, 6, 8. We have 8 bonding electrons. And that means we also have 2, 4, 6, 7 anti-bonding electrons divided by 2. So that will give us 0.5. How do you interpret this? As long as your bond order is above 0, it means it exists and it is stable. So this does exist and is stable. If it's 0, then it does not exist because it is too unstable. One more question that they can also ask you is the first ionization energy. Which one has the greatest first ionization energy? Neon or neon diatomic with a plus? Well, how you interpret this part is you look at their valence orbital diagrams. You see how 2p is lower in energy, like literally lower in the diagram, than the valence of neon 2 plus. What this means is the higher the energy, the higher the orbital energy, the more unstable it is. You see how anti-bonding orbitals are higher than these bonding orbitals. So that means they have higher energy and they're more unstable. There's more repulsion. And if it's unstable, that means it's easier to remove an electron, which means this has a lower ionization energy. Or if you want to look at it from neon's perspective, because it is lower in energy than the valence of neon 2 plus, that means it is closer to ground state. And we know ground state means it is stable. And the more stable it is, the harder it is to remove an electron. So that means this will have higher ionization energy.